Hi, today we will be learning about the one-way ANOVA statistical test. Let's get some motivation. Let's say I have group A and I measure the systolic blood pressure for every person in that group. And similarly, I have a group B and I have everyone's blood pressure measurement in that group. I want to statistically compare the mean of the systolic blood pressure across both groups. So the null hypothesis would be that the mean systolic blood pressure of group A is equal to the mean systolic blood pressure of group B. And my alternate hypothesis is that the means of the blood pressures are not equal across group A and group B. The statistical test that I would use for such a situation would be a two-sample t-test, assuming the samples are independent and not paired. Extending the idea further to two or more groups. So let's say we have four groups, and now I want to compare the systolic blood pressure between these four groups. Meaning I want to see if the mean systolic blood pressure of group A is equal to group B is equal to group C equal to group D. That would be my null hypothesis. My alternate hypothesis would be that any two comparisons from these four, the mean systolic blood pressure is not equal to each other. However, I cannot do the two-sample t-test in this case. I need a more sophisticated method, and now we are going to move towards one-way ANOVA. The one-way ANOVA stands for analysis of variance, meaning we are going to base our analysis on the variance or the spread of data. Particularly, we are going to take a look at the variance in the data by partition. Let's see what it is. Let's first visualize the data. So I have four groups A, B, C, and D. Group A was given a placebo drug to lower their blood pressure. Group B was given the first drug. Group C was given the second drug. Group D was given the third drug. And for every person in those four groups, we are measuring their systolic blood pressure. If I plot the systolic blood pressure from all the four groups, this is what I see. So the blue dots are from group A, the orange dots are from group B, the gray dots are from group C, and the yellow dots are from group D. These are the systolic blood pressure measurements from the four groups. And now, as mentioned before, my null hypothesis is that the mean systolic blood pressure across the four groups are equal, and the alternate hypothesis would be that the mean systolic blood pressure across the four groups are not equal. At least two of them are not equal. Diving in further, so we see that each group has its own systolic blood pressure measurement and has its own distribution. That distribution has its mean and that distribution has its variance. The first thing to notice is that there is mean and variance in the four groups individually, but there is also an overall mean and the overall distribution with its variance, meaning all the points, all the systolic blood pressure measurements collected together have a mean of 126.70. So all the 40 people have a mean blood pressure of 126.70. Now, Group A has a mean of 129.26, Group B has a mean of 127.86, Group C has a mean of 126.63, and Group D has a mean of 123.06. So now you can observe that there is not only one overall mean, but there are four group-based means too. So what does it mean to compartmentalize the variance? The first component of variance is the between group variance, meaning how much of variance is there between the groups. So for that, we are going to see the difference between the mean of each group and the overall mean, indicated by the red arrows. Meaning, we are going to take the difference between the overall mean and the mean of each group A, B, C, and D. This is the generic formula for that. And when I do the calculation, I get a sum of squares, that SS stands for sum of squares, which is the variance between the groups, how far each group's mean is from the overall mean. And the value that I get is 211.73. There is one more piece of information that I would need to collect from this plot, which is the degrees of freedom. So there are 4 groups and subtract 1, so there are 3 degrees of freedom. So I am going to use these 2 pieces of information in the final ANOVA analysis. Now my second compartment of the variance comes from within the groups, meaning what is the variance or spread within the groups. So the sum of square within groups will come from the difference between each individual point and the mean of the group itself, not the overall mean. And this will give us the spread or the variance within each group. This is the generic formula, and I have made a calculation and I get 77.47 as the sum of squares within the groups. One more piece of information to be gleaned from this plot is the overall degrees of freedom, which is the number of points minus the number of groups, which is 40 minus 4 is 36. So just like the previous plot, I am going to take these 2 pieces of information and calculate my ANOVA test. So if we remember from 2 slides before, I had the between group sum of squares and the degrees of freedom. From the previous slide, I had within group sum of squares and their degrees of freedom. Then I calculate the totals. Then I calculate something called as a mean square, which is nothing but the division of sum of squares by the degrees of freedom in each row. And finally, I calculate the F statistic and the corresponding p-value. Note that I am using an alpha of 0.05 for deciding my significance. So here, since my p-value is less than 0.05, I reject the null hypothesis, meaning that the mean of all groups are not equal, or in other words, that any 2 groups have different means. But which are those 2 groups? Is it A versus B, A versus D, or which of those combinations? So now we must statistically compare each of those combinations. And that is called a post hoc analysis. Just as a recap, I wanted to compare the mean systolic blood pressure across the 4 groups, and I rejected the null hypothesis from the ANOVA F test, saying that the mean across the 4 groups are not equal, and thus I now need to perform pairwise comparisons. But how many pairwise comparisons do I make is given by this formula, and in this formula k is equals to 4 since I have 4 groups. Meaning if I have 4 groups, I need to make 6 comparisons, and these are those 6 comparisons. For example, when I compare group A versus group B and I subject it to a 2-sample independent t-test, the p-value that I get is 0.87. But a word of caution is I cannot compare that 0.87 against the 0.05 alpha which I introduced in the previous slide. Now I need to correct this alpha for the multiple comparisons that we are seeing in this table above. The concept of multiple comparisons is beyond the scope of this particular video, but in this situation we would correct our alpha for the 6 tests by dividing the alpha 0.05 by 6. So now the alpha would be 0.00833, and I would compare those p-values from the table above to the corrected alpha level to check for significance, not the 0.05 alpha. I wanted to mention some assumptions of this ANOVA test. The outcome must be a continuous variable. The independent variable must be more than 2 categories or equal to 2 categories. The data should be normally distributed, and there should be equal variances across the groups. What do I mean by that? So I have changed some points in the plot, and now if you see, the variance of group D, those yellow points, is way too large than groups A, B, C. In the previous slides, we had roughly equal variances across A, B, C, D. So this is an important assumption of ANOVA. Finally, I just wanted to give a formula list for the whole ANOVA analysis. Thank you.